So here we're trying to find the surface area of revolution for this shape. I've taken the sine function from 0 to pi, just the first hump of the sine function, and then I spun it around the x-axis, trying to get the surface area here. And again, I'm going to take a physical integration approach to this. I'm going to chop it up into a bunch of tiny contributions to surface area, and then add them all up using an integral. I think I make that mistake 100% of the time. All right, there we go. So I'm going to try to chop this into ribbons. Remember, it's a surface, it's not a solid. All right, so we're slicing the surface into infinitesimal little ribbons. And then if I look at this little width of my ribbon, that's a little chunk of arc. And that's why these two things are usually put in the same chapter in a calculus book. That's a little ds. And the radius of my ribbon, so if I go from, I hope this isn't too obnoxious, but I'm going to put in a little radius here. So from the axis of symmetry out to the edge of this thing. Well, that's just the value of f of x itself, or sine x. All right, and just like we were doing with cylindrical shells, I then slice my ribbon and unroll it. And we'll see what it looks like. Whoa, I'm getting crazy lag right now. Hopefully we don't crash. I think I know it's wrong, but I can't fix it on the fly. So I have a thickness of ds, and then I have a circumference of this guy of 2 pi times the radius, or 2 pi sine x. And then ds, I just used the same thing I was using with arc length. ds is the square root of 1 plus f prime of x squared dx, which means square root 1 plus, well, the derivative of this function is just cosine. All right, and this little area of the ribbon is what I call dA, a differential contribution to the total area. And I'm going to get an expression for dA real quick. dA is just length times width, so it's going to be 2 pi sine x root 1 plus cosine squared x dx. And once you've got an expression for dA, then the integral just simply adds all those up. So I have the total area is equal to the sum of all the contributions to the area. But now I have an expression for that little differential area contribution. And this is entirely phrased in terms of an integration variable x. So I'm going to go from the beginning value of x to the ending value.